It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farming Junior Nice Coffee. Hi guys, welcome to the next video in the naming organic molecules. In this one it's going to be a little bit different. I'm going to go through not only naming and drawing esters, but I'm also going to go through some of the reactions, how we produce esters, and then also how we hydrolyze them, because you need to know some of that in a bit more detail. So if you haven't looked at some of the previous videos about naming, make sure you do that, because I'm going to go through it really quickly. So if we're looking at esters, what we're going to be looking at is this functional group right here. Okay, so we want to be looking at the carbon double bond oxygen, so a single oxygen here. If you're seeing it in a condensed formula, sometimes you see it as this as a carbon with a bracket oxygen and then another oxygen as well. Okay, this is a polar group because you've got these electronegative oxygens in there, but your esters tend to be non-polar because you've got these long carbon chains either side. So very long non-polar sections, very small little polar ester section here. Okay, so they tend to be water insoluble and have lower melting points and bonding points than the alcohols or carboxylic acids they're made from. So if we're going to have a look at an example of an ester, here's one here. Okay, so you see here's our ester functional group, the carbon double bond oxygen and then a single oxygen here, and it's made up of two parts. This part with the double bond oxygen comes from a carboxylic acid, and this part here off the single oxygen comes from an alcohol. We treat this like a side branch when we're going through and doing the naming. Okay, so that's got two carbons, so it gets the side branch name of ethyl. Okay, and then we look at how many carbons we've got here. 1, 2, 3. So we call this propanoate. Okay, so esters always end in anoate at the end of it. And you look at how many carbons there are. 3 makes it propanoate, and the 2 there makes it ethyl at the beginning. Okay, sometimes you might hear this referred to as acetyl or acetyl propanoate. Okay. Ethyl and acetyl are used interchangeably, just as methyl and formyl are. So sometimes it'll be called formal, they have formal propanoate, formal butanoate if it's just got the one carbon here. Sorry, one carbon over here on the alcohol part. Okay. I'll also show you about how to actually draw them. So if we've got this one here, 3-hexyl butanoate. Okay. The first part of the name comes from our alcohol. So the alcohol that this is actually made from is hexanthreol. Now the number is important when you're drawing them. And we've got butanoate. So the acid we're looking at is butanoic acid. Okay. So the way you draw it up is I suggest you put your carboxylic acid group in, C double bond O, then single oxygen like that. It's 3-hexyl, which comes from hexanthreol, which means that the third carbon is the one that actually bonds to the single oxygen. So you put this in, and that's actually your third carbon. So we've got 2 below it here, so it makes it 1, 2, 3, and then we've got 3 more above it. It doesn't matter which way you actually draw it, if you go up or if you go down. So that's actually the hexanthreol component, or the 3-hexyl part of the ester. Butanoic acid means 4, so we've got CH2, CH2, CH3, and the answer 1, 2, 3, 4 here makes it butanoate. Okay, so naming off of this, the alcohol part's fairly straightforward. Alright, you just got to make sure you look at the number, and that's the number that bonds up, or number of the carbon atom that bonds up to the oxygen. I suggest you to find some more either online or through the Essentials workbook or something like that to actually have a go at, and just try drawing in and naming them as well. So what we're going to be looking at is how we actually make these esters. Okay, so if we want to make an ester, okay, there's 2 things we need. We need to add a carboxylic acid, okay, to an alcohol. Alright, so a carboxylic acid plus an alcohol gives us an ester plus water. Okay, now this is actually an equilibrium reaction. Okay, so it means it can go both ways. So what we're going to look at first is the formation of the ester, and then we're going to be having a look at how we can go backwards and taking the ester to get the carboxylic acid and the alcohol, and that's called hydrolysis. Okay, when we form our ester, it's sometimes called esterification. Okay, there's because it's equilibrium, we want to look at things like increasing the yield, but we also want to have a look at the rate as well. So in terms of rate, there's 2 things we use. We generally use an acid catalyst. Okay, we use sulfuric acid normally because the sulfate part of the acid doesn't react. So we've applied H+, that's a catalyst, increases the rate of reaction by providing alternative reaction pathway with lower activation energy. What we also do is something called reflux. Now, reflux is how we supply heat. So that's energy, increases the rate of reaction by increasing the energy of the particles, more frequent collisions, more particles of the carboxylic acid and the alcohol have energy greater than or equal to the activation energy. So we get a increased rate of reaction of our ester. Okay, reflux, I'm going to show you what that actually looks like. So I'll come back to those in a minute. All right, and I'll bring out a diagram of some reflux here. Alright, so for reflux what we use is a pear-shaped flask. Now a pear-shaped flask is called that because it looks a bit like a pear, but it actually helps to actually conduct the heat really well through your solution. You can use a round bottom flask and you'll sometimes see diagrams of that, it doesn't really matter. Okay, we use anti-bumping granules. Sometimes when you're heating up liquids you get little bubbles of gas forming down the bottom. What they can do is they can pop and cause your liquid to splash out. Now that's hot liquid, we don't want to do that, but it's also, we're going to be losing reactants and products if we allow some to come out. So we put anti-bumping granules in, which is normally just fine grains of sand, helps it to boil at a nice constant rate. We heat it up. As it's heating up, our carboxylic acid and our alcohol are reacting and they're forming the ester. Now, the ester generally has a lower boiling point, as I mentioned, because it can't hydrogen bond like the alcohol and the carboxylic acid, so the ester starts to bubble as it's formed. If we don't condense it back to a liquid, our ester is going to escape. So what we do is we put a condenser on here that cools down the vapours, puts them back into a liquid form, it comes back down and it's allowed to continue to react. Okay, so that helps to increase the yield of our ester because we don't allow any of our volatile components to escape. If we boil the alcohol or the carboxylic acid and that escapes, that's going to reduce our yield as well. So if we heat it for about 35 to 40 minutes, the heat increases the rate of reaction, but also the fact that we're using the reflux allows it to go for longer, which increases our yield. So, if you wanted to create this one here that we had a look at, which was ethyl propanoate, we take some ethanol, we take some propanoic acid, we put it in a pear-shaped flask, we'd add in a couple of drops of sulfuric acid, we'd set it up to reflux for about 35-40 minutes, and then we'd have our ester here at the end. Plus we'd have some other components and we can separate them out using some organic separation. The ester is normally very water insoluble, so that would form a separate organic layer, okay, and we can extract that. What I said though is that we can go backwards, so if we can actually take an ester like this and go back to form our alcohol and our carboxylic acid. Okay, so instead of going like this, where we have our carboxylic acid plus our alcohol, and we form our ester plus water, okay, instead of going that way, what we do is we actually swap it, and we go ester plus water, and we form our carboxylic acid and our alcohol. Alright, now there's two ways that we can do this. Okay, the first one is by what we call acid hydrolysis. So hydrolysis is adding water back in. It's acid hydrolysis, so we use an acid like sulfuric acid again, and it's just a reverse reaction. We get our carboxylic acid and our alcohol formed, we still have some ester and some water in there, and we try to separate them out. An easier way to do it though, instead of acid hydrolysis normally, is by doing what we call alkaline hydrolysis. Now, alkaline hydrolysis is a little bit different because we use a water-soluble base, okay? And that changes our product slightly. Instead of having a carboxylic acid, we now end up with a carboxylate ion, okay? Now, a carboxylate ion, the only difference between that and our carboxylic acid is that we've deprotonated it. Because we're doing it under alkaline or basic conditions, the base reacts with the acid, gets rid of the proton there. Okay, so I'm going to show you what that actually looks like. So, if we take our ester that we've been looking at, our ethyl propanoate over here, okay, if we do that under acid hydrolysis, we're just going to end up with our propanoic acid, okay, and we're going to end up with our ethanol that we originally started with. Okay, that's acid hydrolysis, just the reverse of making the ester. If we did it under alkaline hydrolysis, however, okay, the main difference is that we now deprotonate that because it reacts with the base. We end up with the negative carboxylate salt, and because we normally use sodium hydroxide, we end up with the sodium form. Now that's important because what that does is that actually makes our acid now water soluble. The iron dipole interactions between the sodium and the water means that's quite soluble. If we get a slightly longer alcohol, such as butanol or going into pentanol, that's water insoluble. So our ester and our alcohol are water insoluble, so we can extract them out using a non-polar solvent, alright, such as hexane or something like that, okay? And that leaves just our water-soluble acid with some water. Now, what we then do is we then react it to convert it back into just the carboxylic acid. It is no longer water soluble, so we now end up with two layers again, an organic layer which has the acid and just the leftover water from the reaction, and that way we've separated or isolated our carboxylic acid, which is quite more useful because that's generally what you want to go to, and we can extract the alcohol from the ester. So I know I've gone through a lot of stuff and I've gone through it pretty quickly. Alright, so what you want to get out of this video, and you might need to go back and have a look a couple of times, is a couple of things. So make sure, firstly, that you can, draw esters. Make sure, number two, you can name esters. Okay, number three, make sure you know how you form esters. So going through, and you want to be able to talk about reflux. Alright, you want to be able to talk about rate and yield in terms of ester formation and what affects it. And number four, you want to be able to talk about hydrolysis. Okay, and you want to be able to know the difference between an acid and an alkaline hydrolysis. Okay, and you want to be able to talk about the carboxylate salt. Okay, so you're going to have to look at this probably a couple of times. Practice drawing and then naming them, okay? And then make sure you understand the difference between hydrolysis, and you can explain reflux and some of the factors for esters, alright? Hope this is helpful. Ask me if there's any questions. Thanks guys. See ya.